going to talk about how right now at the University of Rochester, I'm kind of doing research related to eye tracking. And we're going to kind of see how we can, different ways in which we can apply machine learning here. And yeah, it's kind of cool. So just a quick background about me. I did my undergrad at Harvey with got my bachelor's in engineering. And then after 4 years of college, I was kind of tired and I realized that I didn't think I'd want to go to school again. So I went to Northrop and I started working on a GPS related satellite as a hardware engineer. And I kind of seeing that I actually learned a lot more, realizing that I actually learned a lot more than I thought I did. When you actually apply, you kind of realize that. And I wanted to go back to school then. Kind of motivated me to go back. And I kind of wanted to change fields also to a more medical, like biomedical field. And so that's sometimes the motivation to go back because you want to change your field. So I went back to Stanford and got my master's in electrical engineering. And when I was looking for jobs, I kind of wanted to do research, but I did not want to really do a PhD. And what I found out is that universities actually hire into labs. So that's actually an option for some people as well. And that's kind of cool. That's what I'm doing right now. I'm a full-time engineer at a lab at the University of Rochester. So all my coworkers are actually PhD students, but I don't have to do, I can kind of get involved with the research, but not necessarily a full PhD. If you don't want to do the full course, you can kind of just get hired in as an engineer. So that's kind of an option as well. Okay, so let me just start with the question. What is eye tracking? It's kind of tracking your eye movement to get an idea of where you're looking. And that's kind of what we mean by eye tracking is when we study it and when we're trying to use it for things. So we start with an image of the eye, and we kind of get these landmarks, kind of like facial recognition, where it could be the pupil, it could be some other landmarks that you're trying to figure out. And then from that, you get an idea of rotation, and that will tell you where you're looking. So you're looking at the bear, you're looking at the blanket. That's what eye tracking will be able to tell you. So why do we need eye tracking? What are some uses? Yeah, so here's some of the applications I came up with. And at the bottom, you see that someone mentioned driver attention detection and just kind of where you're looking while you're driving. VR, right, exactly in the top left. So there's something called foveated rendering, which is kind of where you're looking. They render based on where you're looking. And on the top right, you can see an augmented reality situation where based on where, and we have this with our phones already, but imagine if you don't necessarily need your phone, based on where you're looking, if you're looking at the t-shirt, it kind of labels it as t-shirt or it gives you some other information about what you're looking at. And also in surgery. In fact, this is also what I have depicted here is kind of also an augmented reality situation. Where augmented reality, for those who are not familiar, is just basically you're kind of augmenting your real space with some sort of virtual display or virtual something. And so on the bottom right, you can actually see an augmented reality surgery situation, but it's actually also used, eye tracking is also used right now in training of surgery. So they can kind of get an idea of how well someone understands their procedure based on how their eye moves and what they're looking at. And that's actually some research that's going on over here as well at the University of Rochester. So that's cool. Okay, so how do we track where the eye is looking? And this can be kind of boiled down into a few steps. Essentially, we have an eye and there's this arrow which kind of serves as like a vector or where the eye is pointed. And then we're trying to figure out this gaze point or this red dot. So as the eye moves, the gaze point obviously changes because where the eye is looking changes. So that's how you can understand that if we get an idea of your eye rotation, we can get an idea of where the eye is looking. So the step one would be to determine this eye gaze vector. And that's kind of where a lot of the brains are. And it's kind of where a lot of the algorithms are targeted because that's kind of difficult kind of to understand how we can identify where the eye is looking based on the eye rotation. And then step two is to map it onto a gaze point in space. This is not trivial either, but it's a little bit more straightforward. You kind of it's more linear algebra, just following that line and figuring out where it is in 3D space. For this talk, I'll focus on step one, and we'll kind of see where we can apply machine learning here. All right, so option one, it's like, this is a common method. I'm going to talk about two options. One is what research we're doing right now, and this one, which is pupil-based methods, is kind of what is used in commercial items right now. So Pupil Labs and Tobii Pro are two eye trackers that you can actually buy yourselves right now, and they're relatively cheap. And what they're based on finding the pupil. So if we can find this, where the pupil is, you can find the center and you can figure out where it's looking. So let's simplify this problem to an ellipse. So essentially a circle is a generalized, or an ellipse is a generalized circle. So if A and B, which are the radius, are equal, then we have a circle. So if we can figure out C, which is the center of that ellipse, A, which is the major axis or the longer axis radius, and B, which is the minor axis radius, we can theoretically draw out the full circle and identify where, or figure out where someone is looking. So let's say that the goal is to find A, B, and C. So if we start with the image of the eye, we figure out C, A, B, and C for this eye, and then we can get the pupil, and we know where it's looking. So how can we apply machine learning here? What are some of the things that we've learned so far? First, tell me if this is a classification or regression task, and then maybe talk about an algorithm that we've learned last week. Maybe some of you have touched it in your projects this week that we could use for this. Regression. Yeah, exactly, right? Because A, B, and C can take on any value, right? Right, so it can take on any value. We're not trying to classify any categories. We're just trying to understand or to figure out what the values are. Right, okay. So now what algorithm could we use? What's an example of an algorithm? The hint is this is kind of a computer vision task because we have an image that we're trying to process. And what's typically used with images? Train and test data, right? So that's related to splitting the data to that. So that's right before we apply the algorithm, which would be a CNN, right? Convolutional neural net is a common algorithm. Exactly. So we could use, that's just one. You could use a bunch of different algorithms, but for this, I just kind of demonstrating a CNN, which would be the obvious an obvious algorithm to use. And so we could use a convolutional neural net to predict A, B, and C and complete this task. And then we'll get an idea of your where your eye is looking, and therefore the gaze point. All right, awesome. So, and again, this would be a regression task, right? Because we're trying to predict A, B, and C, which can take on any value. So here's option 2, Dual-Purkinje imaging, which is kind of what we're doing right now. And it actually has a lot of benefits over pupil-based tracking, although the optics make it a little bit difficult to make it a commercial product at this point. So that's kind of what we're working on. So what are Purkinje reflections? Now, it sounds kind of complicated, but it's really not. All it is just if you have like a light source that's pointed at your eye, right? It's a directional light source, so everything is in one direction. It's not like moving out. The rays of the light aren't moving out in a bunch of directions. So we're just going in one direction. The reflections off of each, and so this is a cross section of your eye. So in the front of the eye, you have the cornea, which is the front surface. And a little bit further back, you have the lens, which is actually what focuses any light coming in your eye onto your retina, which is how you see. So the light source that you're pointing at your eye, it's kind of like a laser, a low powered laser, because we're not damaging the eye. It reflects off of each surface. So the front surface of the cornea, there'd be one P1 reflection. So that's the first reflection, or the first Purkinje image. And then the reflection off of the back surface of the cornea gives you P2. And then the front and back surfaces of the lens gives you P3 and P4, which are your 4 Purkinje images. Now, to get an idea of rotation, we focus on the first Purkinje image and the 4th Purkinje image. So on the right, you can kind of see 2 of those reflections. So this is this reflection off of the same light source, but the front surface is this big circle over here, and the back surface of the lens is this tiny circle over here. So those are your P1 and P4 reflections. If you get a different, if you can calculate the distance between these in pixels, so this is just an image, and all we're doing is finding the X distance and the Y distance between these pixels, you can get an idea of your X and Y rotation of the eye, which is actually pretty cool. It's such a simple thing, and that it gives you a pretty precise understanding of your rotation of the eye. So here's like an example video of tracking in real time, and you can kind of see as the eye rotates, the distance between P4 and P1 change. And there's very slight distance differences, but you can actually get a resolution of eye rotation to 1/60th of a degree, which is pretty impressive. And this is actually a very slowed down video. The eye is actually moving much faster than this. Yeah. Okay, so again, remember we're trying to figure out this eye gaze vector. So if we have an idea of the rotation, we figure out this eye gaze vector, and then we know the gaze point. So in this case, we're trying to figure out, find the P1 and P4, and then find the distance between that, and that's how we get our gaze point. So what about here? How can we apply machine learning here? It's a little bit less straightforward. I'm going to give you a few hints. So here's an image, right? It has no information about it other than the pixels. We don't know, I mean, we can see where the P4 and P1 are, but the computer doesn't know that. So, and we don't have a labeled data set. So it's unlabeled, which means we might be using some sort of unsupervised learning to first find these clusters. K-means clustering, so if we set K equals to 2, we can actually tell it to find 2 clusters. And what we're looking at here are just these intensities of the pixels. So just find 2 clusters of high intensity pixels. And that way we get P4 and P1. And then from this, we can kind of crop these images. And then what can we do? So this is now, we're trying to identify which one is P4 and which one is P1. So what kind of task would this be? Classification, right? And again, any algorithms, we can kind of use the same one already. So if we can get, this is again, yeah, right. We can just use a CNN again, right? We can use a convolutional neural net to then classify. And then we identify which one is P1 and which one's P4. And for this one, we would need a labeled data set that we should have a model that we could have trained on a data set already. So then we just give it a bunch, we just give it 2 things, 2 images that are the same size, identify which one's P1 and which one's P4. And then we come back to this image. Now we know where the P1 is and where the P4 is, and we can get that distance, which is just simple simple difference arithmetic. And then we get an idea of where the eye is looking. So that's kind of like a simple way to apply machine learning in some state-of-the-art research, which is actually pretty cool. And you can already do this with the stuff that you know.